Physics paper 2 for the year 2021 is what's up. Starlight fades in light years. Children of light we are. Allow me to get to question 1. Okay, there we are. So the first question reads, figure 1 shows a metallic pyramid of equal sides, 20 centimeters long, resting on one of its sides on a flat surface. Okay, so this is our metallic pyramid of each side. Each edge is 20 centimeters. Therefore, these are more like equilateral triangles that have been made to make one pyramid. Some pyramids have got rectangular bases, some have got triangular bases. So the first question reads, A1, state the quantity that should be measured on the pyramid to determine its volume. My answer here is space. Okay, the space it occupies, or the 3-dimension space, or you can even say 3-dimension space it occupies, but the keyword here is space. Okay, if you measure the space that an object is occupying, therefore you are actually measuring its volume. So the question is, state the quantity that should be measured. The quantity is space. The measure of space occupied by an object is called volume, and that's actually a physical quantity. A2, calculate the volume of the pyramid. The formula for volume of a pyramid is this: V is equals 1/3 area of base times the height of the pyramid. I was almost going off key because I was able to calculate the area of the base, which is area of a triangle, because this has got a triangular base, and look at all the sides are 20, all the edges are 20, so half times BH. So I was able to calculate for the height, which is his here. I was almost cancelling it, but this is how I found my height. I was almost cancelling it because I became a little bit confused. I used the same height of the triangle by, I applied it here. Okay, let me just say this is how I found my height. I shouldn't have cancelled it, so that I maintain it for the sake of knowing where I got this 17.32. So the edge, the base of the triangle, we're looking for the area of this triangle. All the sides are 20, and this is the base of this pyramid. So the base is, if we're to make this triangle stand up, okay, be upright, this would be, for example, our base. Then we will need the height of this triangle, the base. Therefore, the height is what I calculated like this. Height is equal to A √3/2. My answer came out, our A is the side of that triangle. Okay, it's equilateral. So my answer came out to 17.32. So this is the height of this triangle as I calculate for its area. So my H comes out as 17.32. Then the base is 20. Then this is our constant, which is a half. So the area comes out as 173.2 centimeters squared. This is 20 centimeters. This is 17.32 centimeters, the height. So centimeter here times centimeter here gives you centimeters squared. So this is where my area is. This is our constant, which is this. And now I want it, or I'm supposed to look for the height of the pyramid. Therefore, the height of the pyramid from this center here going upwards. So I became a little bit confused and wanted to use the height or the length, therefore the height from this middle part here going upward like that. Therefore, I became confused and used this quantity here and placed it there. But later on, when I was going through before recording, I realized, oh, I made up. That's what made me cancel this here. But otherwise, to calculate for the height of a pyramid with the triangular base made of equilateral triangles, the formula to calculate for the height of this, therefore from this central part going up to this apex here, the formula is what I finally gave here, which is H is equals to √6 times S, which is the side, okay, the side or the edge, which is our 20 here, which is this 20 over there. So √6 times S over 3, or √6 over 3 times S, which can be something like H is equal to √6 over 3 S. Okay, so it can even be written like that. So this is the constant. 20 is the side, which is the 20 centimeters. So the height of the pyramid is 16.33 centimeters. So I plugged it here and removed the 17. Yeah, it's a little bit dirty, but I plugged it here and did my calculation. Centimeter times this centimeter will give me centimeter cubic. This times that gives me 942.8 cubic centimeters. That is our volume, 942.8 cubic centimeters of volume. So understand the formulas. Look at this volume of a pyramid with a triangular base, then area of the base, which is this A, then H is this here, the height of the pyramid. And in the process of finding area of the base triangle, or the base, which is a triangle, you will still need its height, and this is the formula for finding the height of a pyramid or of this nature. So mathematics becomes an important key here. So I move to the next question there. Wow, one question, five minutes. Let's see if I can do 5 questions or so. Figure 2.1 shows a velocity time graph for a body in motion. Sewe says life is motion. Okay, life is motion. Anything that has life has to show some movement through growth or movement or locomotion. So shows a velocity time graph for a body in motion. So this is our time graph. This body was already moving and it was already at 4 meters per second squared, because this is volume, this is velocity. Then it just changed or increased its volume uniformly to this much, which is this much. So it increased from 4 to 8. In how many seconds? From 0 to 4, therefore in 4 seconds. So A is reading as follows. Explain what is meant by uniform velocity. Okay. My alternative way of explaining this term here is uniform velocity is constant rate of change in velocity of an object, therefore constant rate of change. I'm not specifying whether increasing or decreasing, because uniform velocity can be uniform velocity which is resulting into slowing down, or uniform velocity which is resulting into increasing velocity. Okay, because change in velocity is acceleration, so it can be acceleration or deceleration, but uniform velocity is constant rate of change of velocity of an object. The moment I say rate of, therefore constant change with respect to time. Okay, so that's my explanation there. Explain what is meant by uniform velocity. B, describe the motion of the body from A to B. Its velocity was steadily increasing at constant acceleration. Okay, I don't know if I came out clear there. If you look at this graph here, the velocity was steadily increasing at constant acceleration. Okay, meaning at constant change of velocity. So its velocity was steadily increasing. I was running out from this word uniform. Steadily increasing, meaning stable. It is stable in its increase. You can follow it. The moment I say acceleration, therefore with respect to time, so its velocity was steadily increasing at constant acceleration, constant rate of increase of velocity. Finally, C, calculate the acceleration of the body. You should know formulas. So acceleration is equal to final minus initial over time taken. So when you look at this graph here, our initial was 4, and then our final is 12. In how many minutes? In 4 seconds. So 12 minus 4 gives me 8 meters per second. That was the change. Over 4 seconds, giving me 2 meters per second squared was the rate of change of velocity, or it was the acceleration. This formula can also be written as A is equals to change in velocity over time taken. Okay, you can even say change in time. You can put delta t here, but it's the same as this one here. So our answer was 2 meters per second squared. I flapped them pages. D, on the grid in figure 2, plot a distance time graph for the motion of the body. Okay, for the motion of the body. This is our last part here. Distance time graph. Okay, so meaning distance should be on your y, then time should be on the x. Therefore, how far did it go in the 4 seconds? How far did it go in the 4 seconds? I had to do some side calculations. Unfortunately, I don't have the paper right now, but I had to do some side calculations where you determine how far the object or the body moves in the 4 seconds when its acceleration is at this rate. Okay, there we go. To recalculate this so that I don't just speak from without. This is although supposed to have a title, but a distance time graph from our question there. And how did I find the distance? I had to calculate the distance it moved in 4 seconds when given initial final velocity, and I also have acceleration which I calculated. So I use this formula. Displacement is equals to initial velocity plus final velocity in brackets, then times time taken, then over 2. Then I had to replace the variables. It gave me 32. You can either use this formula, it will give you the same answer, or use this other formula here to still give you the same answer, 32 meters. So I plotted my graph. In 4 seconds, this is distance in meters, and this is time in seconds. So in 4 seconds, this is what was covered. There was an increase, okay, uniform rate of coverage of distance because there was uniform acceleration, or there was a uniform velocity, okay, not constant but uniform. Okay, constant is different from uniform. So our answer is, our graph will appear something like that. There was constant change in the y, meaning the object was on the move, and its movement was kind of uniform. Every second there was a uniform increase of 8 meters, a coverage of 8 meters every second. After 4 seconds, it covered about 32 meters. If I'm wrong there, you can still calculate, because at first I don't know how I found my 48, but you go through that. But that is my answer there. Question 3. Figure 3 shows a girl of mass 40 kilograms sliding down a frictionless curved track of height 3 meters in a play park. That's a girl, okay, 3 meters high. These are the stairs or steps. She reaches it and slides like a banana. So the girl slides from C and reaches the bottom. Reaches the bottom of the track at D. Take G to be 10 meters per second squared as our acceleration due to gravity. So girl, let's look at this. 3 meters high, from C to D, and that's the girl there in motion. Let's look at the question. I move the paper. Calculate the girl's potential energy at C. I move the camera. Apparently this small phone has no pause, so I'll just be moving there. So at C here, we are going to calculate the potential energy. The second question is calculate the kinetic energy at D here. Okay, since this is a frictionless curve, we'll take it that the girl will be at her maximum speed here. Here, she hasn't yet begun sliding, so we'll calculate her potential energy, quite right. Then here, as she slides, since this is where this slide ends, we'll take it to say on this slide, her maximum speed was reached here because she kept on accelerating at this rate. Therefore, her speed kept on increasing as she was falling up to this point. Therefore, at this point, she was at her highest speed of sliding. So, formula for potential energy is mgh, where mg is weight. So, you can even write wh here. Her mass is 40 kgs, gravity is 10. Then here, I was almost writing 30. I don't know where I got the 30. That's why my answer came out as 12,000, but I quickly saw it. So it's actually 3. The height of the ramp or the slide is 3. So when you look at this, there it is. It's a 3. So when you multiply this, remember to include the units, okay? Okay, let me just say we should be including units, because sometimes even me actually for victim, I just calculate like this but give the correct units at the end. But let's cultivate a culture of as much as possible to make the physics real. Include the units. So 40 kg times 10 meters per second squared times 3.0 meters. Okay, so this will cancel out with this. You're going to range it kg per second squared, something like that. So PE, or potential energy, is going to be equal to 1,200 joules. You're calculating for energy. So after you multiply this, it should give you 1,200 joules. That will be the potential energy on top there. Number B, calculate the energy at D when she was falling at the base of the ramp at her maximum speed. The formula for kinetic energy is Ke is equals to half mv squared. Okay, so our half is a constant. M is the mass, which is 40 kgs. Then this, I was almost getting it wrong because I went on with a 30 here. So for me to calculate her speed of falling at point D here, her speed at her maximum speed I need to calculate using this formula here. Velocity is equals to root 2gh, the velocity of a freely falling object, where h is the height through which the object has fallen. Okay, so we're having 2, which is a constant, 10, which is our g. Okay, our g, then 3, which is our height. Okay, through which she has fallen. So when you multiply this, it will give you 660. Okay, because it's now a 33, not 33. So it comes out as 60, not 600. It's 60.0. Then the final velocity that she will have will be 7.746 meters per second. So coming here, we plug in the velocity, which is 7.746 here, then we square it. Okay, because on the formula it's half mv squared. Once you square it, it will go back to 60. So it's going to be 60 times 40 times half. Okay, so 40 times 60 gives you 24,000 times half gives you 1,200. Oh, okay, I think I messed up here. Allow me to just correct it. It's not supposed to be, because half of this is 12,000. So I think I just cancelled here. I didn't cancel here. I hope you're following even in my mistakes. So okay, let me just pause a little bit and just rectify this. So there we go. I maintained the 24, but it's supposed to be 2,400. And I was just doing a little bit of confirmation somehow. So this is 2,400. Okay, ignore this comma here. So 2,400 times half will give you 1,200. So the kinetic energy she was possessing as she was falling at point D was 1,200 joules. Okay, 1,200 joules. So yeah, I know you're able to see. Okay, I know, because I've rubbed here, I've rubbed there, and here, so it doesn't look so neat, but you are able to see, right? You can pause and just look harder and even recalculate if you like. So now the last one is speed at point D. I just go back to this calculation here. The speed of a freely falling object. I'm calling it speed of a freely falling object because the ramp was, or the slide is said to be frictionless. Okay, frictionless curved track. So the answer comes out as 2gh, 2 times 10 times 3, the height gives you 60, root 60 gives you 7.75 meters per second. That was a speed at D. Allow me to flip a page. Question 4 right there. Question 4 shows, figure 4.1 shows ultrasound being used to produce an image of the heart. So this heart almost looks like a carrot, but that's the heart. Then the probe, then ultrasound waves, ultrasound transmitter and detector, therefore encoder and decoder. So A, define ultrasound. My answer, this is grade 11 physics, sound, topic sound. Define ultrasound. It is sound whose frequency is above the hearing range of the human ear. It's called ultrasound, or sometimes referred to as sonar. Okay, yeah, ultrasound, sonar, you can call that. So B, explain how particles in the human body move as the ultrasound passes. You have to know the type of wave that sound is. Is it transverse or longitudinal? Sound waves are longitudinal in nature, and longitudinal waves cause particles of the media through which they are passing to vibrate parallel to the direction of the wave energy. So my answer here is they vibrate parallel to the sound wave direction. They vibrate parallel to the sound wave direction. C, the distance between the heart and the probe is 10 centimeters. The speed of the ultrasound in the human body is 1,500 meters per second. Calculate the time taken for the ultrasound to move from the transmitter to the heart and back to the detector within the probe. Time taken. Remember that here we're talking about speed of sound using echo method, because for this probe to receive back the image and all that, for it to create an image, there has to be some echo that has to bounce off certain organs, and the specific organ in focus here is the heart. So we are determining speed of sound using the echo method, and the formula is S is equals to 2D over time, where I make T to be my subject, therefore 2D over speed. The speed is given to us as 1,500, which is this 1,500. Then the distance, here we're given distance in, where is that? What? The distance here is given to us as 10, I think I saw it 10 somewhere. Okay, it's here. The distance between the heart and the probe is 10 centimeters. We're talking about meters per second, but this is in centimeters, so we convert it to meters. So it's 10. When 10 centimeters is converted to meters, it gives you 0.1 meters. But since the sound has to travel to and from, to and from the probe, it has to be emitted, bounce off, and travel back. It covers the 10 centimeters twice. So going 10 centimeters, coming back 10 centimeters, giving us 20 centimeters. So I have to multiply this by 2 because it's distance for going and coming. So the distance is covered twice. So it comes out as 0.2 meters. You can just include the meters there. Over 1500 meters per second squared. And the answer comes out as 1.33 exponential negative 4 seconds. Or times 10 to the power negative 4 seconds. That's the time that the sound takes to move to the heart and back. Time taken for the ultrasound to move from the transmitter to the heart and back to the detector within the probe. So the time is 1.3 exponential negative 4 seconds. We'll go to question 2. Frequency of the ultrasound having a wavelength of 1.2 exponential negative 3 meters. I was almost using this formula, then before I could even go any further, I realized it can't apply, but that's one of the formulas that can help you calculate for frequency. So I went to the wave equation. I've been given velocity of sound. I've been given wavelength, which is this, so I can find the frequency. I make f the subject by dividing by lambda or wavelength on both sides, and it gives me frequency is equal to velocity over lambda or wavelength. So velocity I'm given is 1500 in the question. Then the wavelength is this, so my answer comes out as 1.25 exponential 6 Hz. Or you can express it in its fullness of 1000, this was 1.25 exponential 6 Hz. And then you can write it in its fullness as 1,250,000 Hz if you like. So always write your formula and substitute them with the correct values, with correct units, and finally do your calculations properly. So here the key thing is know how to punch the calculator when it comes to exponents and the like. So our answer is 1.25 exponential 6 Hz. Get to question 5. A 1 kg mass of water in a kettle is heated by an electric power of 1000 watts to increase its temperature from 20 to 90 degrees Celsius in 5 minutes. Is heated by an electric power. So specific heat capacity of water is 4200 joules per Kelvin kilogram. Calculate the energy released by the heater. So this minus kg or kg to the power minus 1, Kelvin to the power minus 1 can also be written as 4200 joules slash kg Kelvin. It can also be written like that, and it can also be written like this. So calculate the energy released by the heater. Remember that, or take note that wherever you're calculating for work is only done when energy is converted to the amount of, from one form to another. Without conversion of energy from one form to another, work cannot be done. And so whenever energy is converted to one form to another, from one form to another, work is done. The amount of energy converted from one form to another is equal to the amount of work done. So if 50,000 joules is converted to another form, then it means the amount of work done is 50,000 joules. So wherever there is work in any of the formulas you come across, the work can be replaced by energy. So power is equal to W over T, therefore power is equal to energy over T. Because the amount of work done is equal to the amount of energy transferred or converted. So they can be swapped there. So when I make E my subject, it comes out as energy is equal to power times time. Power in watts, which is this 1000 watts. Then time is given as 5 minutes, but we measure time in seconds. So I convert the 5 minutes to seconds, giving me 300 seconds times 1000 watts. And finally, my final amount of energy is 300,000 joules. 300,000 joules. Number 2, calculate the energy absorbed by the water. Calculate the energy absorbed by the water. You're supposed to know the formula for specific heat capacity. So specific heat capacity is equal to energy. This is Q and this is theta. Some books will put T here. So energy over mass of the water in kilograms times change in temperature. Remember, temperature is measured in Kelvin, and even here you're having Kelvin, but here they're giving you what? Celsius, meaning it's not really about the the measure or the scale being used, but the change. You're looking for the change, not the actual temperature, but the change in temperature, because an increase by 2 on the centigrade scale will also result in an increase by 2 on the Kelvin scale. So we're looking for the change. So worry not about that. So we're having this, so we make energy to be our capital, okay, or subject. So energy is equals to specific heat times mass times change. This is delta, change in temperature. So for the 200 joules per kg Kelvin, which is this here, which I was explaining to you, given to us right there, times 1 kg, the water is actually 1 kg there, which is the mass in kilograms, times 70. I just did some subtractions. 90 minus 20, that was the change. The increase from 20 to 90 is 70. So I did some subtraction to give me this here. Yeah, I can put Kelvin here, I can put degrees Celsius, there's no problem, because I'm looking at the change. Then finally, when I multiply all these, I'm looking for energy, then the answer comes out as 294,000 joules. That was the energy absorbed by the water. Energy released by the heater is 300 joules, okay? And then the energy absorbed by the water is 294,000. Here, this is 300,000. Finally, the question follows, explain the difference, if any, in the values of energy calculated in A1 and A2. There's a difference of about 6,000 joules, okay, 6,000 joules. Okay, so why that difference? You have to somehow have a reason why you are likely to have a less amount of energy absorbed by the water. So my explanation is about 6,000 joules of heat emitted by the heater is absorbed by the kettle and partly, supposed to be partly, look at me, partly lost to the environment. So we cannot just say it's absorbed by the kettle or absorbed by the body of the stove, but so you're supposed to show that it is lost in some various forms. So among the main forms is lost to the kettle, because before the heat reaches the water inside, it has to warm the wall of the kettle first. So partly is absorbed by the kettle and partly lost to the environment. Okay, lost to the environment. That's my explanation there. Okay, I flip them pages. No pause button for this camera. So number B, figure 5 is a graph of results of an experiment on the specific latent heat of fusion of water. That's our graph there. This is temperature at 100. This is mass times specific heat capacity times change in temperature, okay? This is mass times specific heat capacity, okay, of water. These are formulas, okay? This is a formula for energy here, and it is a formula for energy at this point given to you. Latent heat of vaporization, okay, LV, latent heat of vaporization, meaning this is the boiling point of water. So the amount of heat that would be required to evaporate a given quantity of water is referred to as latent heat. Then the amount of heat required to evaporate 1 kg of water at its boiling point at constant or at 1 atmosphere is referred to as a specific latent heat. So there's latent heat and there's specific latent heat. When you just say latent heat, it means any amount of water. If you say specific latent heat, then you're talking about 1 kg at 1 atmosphere of pure water at its boiling point. Okay, I zoom in. Taking the specific heat capacity of water to be 4,200 joules per kg Kelvin, the latent heat of fusion as 2,300,000 joules per kg. Calculate the energy required to raise the temperature of 1 kg of water from 0 to 100. You already have the formula here. So mass you have been given already. It's already at the back of the question there, 1 kg. Specific heat capacity 4,200. Then change. Okay, this is delta theta. Or change, I should have put T here. It's something. It's this thing here. So 100, from 0 to 100, the change there is by 100. My answer comes out as 420,000 joules is what would be required to reach that much. But understand that under normal circumstances, you may use more than this because part of the energy you supply will be lost in other forms. So this is just a specific, provided you're not losing heat in any form to any other object or environment. Number 2, change 1 kg of water from 0 degrees to steam. Okay, so they want now the energy. Okay, calculate the energy required to change 1 kg of water from 0 degrees to steam. Here it was just from 0 degrees to the boiling point. Now here this is now encompassing this part here from 0 to 100. Then at the boiling point, which is this formula here, mass times latent heat. So this is the energy. Energy is equal to mass times latent heat of water at the boiling point. So I need to calculate for this because this I already have, because the question is demanding for change of 1 kg from 0 to steam. Therefore 0 to boiling point and boiling to the point where all the water gets to be evaporated. So here 1 kg is the mass, then this is our latent heat, which is 2,300,000 joules per kg. So the answer comes out the same because the mass is 1 kg. So this is the mass that this 1 kg, this is the energy that this 1 kg would require the moment it reaches this point here. Okay, but from 0 to 100, the energy required would be this much. Then the moment it reaches 100, the energy it requires to boil through now, for it to boil, all of it to boil to the point where it finishes, because you have to keep on supplying heat. There won't be increase in the temperature because it's latent. Okay, latent means hidden heat. So you have to keep on supplying heat until it boils and evaporates all of it. Now, how much energy do you need to supply for all the water to boil to the point of it finishing? And that's the energy that we have found to be this much. So now, from 0 to steam, I get this. This is from 0 to 100, and this is from 100 to steam, because it remains constant at 100. So at 100 degrees, for it to boil to completion, to be turned to vapor, you need this much. So I just add this plus this to give me 2,720,000 joules is what is required. 2,720,000 joules is what is required. C, state one factor that does not affect the specific capacity of a substance. Its volume. Okay, its volume. Okay, whether it's half kg, whether it's 2 kg of water, the specific capacity will always be constant. I move to this question, which is question 6. Figure 6.1 shows a ray of light in the air striking the vertical side AD of a rectangular glass block at an angle of incidence 50 degrees. Yeah. So this is 50 degrees. This is our normal. The dotted line is normal. Understand that the angles are measured against the normal. The arrows show the direction of light. This is our glass block, and this is a ray showing the incident ray inside the glass. The refractive index of glass is 1.5. The light travels in the glass and strikes AB at Q. So it travels here and strikes this side AB at point Q, and this is our normal now. So question A, give a reason why the direction of light changes when it moves from air to glass. Because of the difference in the density between the two media. Density is what causes light to bend and even to slow down sometimes. Let me just say, even to slow down, to change speed. Light is fastest in a vacuum. And then as you introduce it to air, to water, to glass, it tends to slow down. And if you finally shine it on a wall, it will actually be blocked. It will be stopped because walls don't allow light to pass through. So it will just be there. It will be hammering on the wall, and it will not pass through. Even in water, the deeper you go into the ocean, the more light finally fails to penetrate through. But if all the water was to be removed from the Red Sea, the light would finally reach the bottom of the ocean. So you cannot see at the bottom of the ocean because of the density of the water. The density of the water, the quantity of the water, in short, the thickness of the water. Okay, let me just get back to this. Because of the difference in density B, at the point where the light enters the glass, the angle of refraction is R. Calculate the value of R. You have to know the formula for the how to calculate for refractive index. The refractive index is the value that represents the degree to which light is bended by a given material. Okay, as it moves from a less dense material to a more dense material. So it's a value that signifies the bigger the refractive index value, the more light is bended. The smaller the refractive index, the more light passes through without being bended so much. So the formula is refractive index is equal to sine I over sine R, Your sine I should always be the angle on the side where the medium has got less density. Sine I over sine R. So we're looking for R there. So we've got, I make sine R the subject by rearranging it like this, cross multiplying. So I'm having sine R is equal to sine I over refractive index. Then sine R is equal to sine 50 because I is the angle of incidence, which is this 50 here, the 50 right there. So here I'm having sine 50 over 1.5, and then I divide by sine on both sides, which gives me sine inverse, so that I can, so that I can just remain with R, angle R by itself here. Sine inverse is equals to this value here, which is sine 50 over 1.5. When I divide this, it gives me this much. So before you arrive on your final answer like this value here, before you arrive here, get everything. Sine 50 gives me this much, and if you have to write it down, write as many digits as possible. Don't just write 0.7 or even round it off to 0.8. It will give you a very deviated final answer. So after I write all of this and I divide, and then I pick all of this, sine inverse, which is shift sine on the calculator, then punch in this number, the whole lot of it, then your answer comes out as 31. The angles, you round them off, don't give decimals. I think it's more appropriate to round them off. My answer comes out as sine R is, R, the value of R is 31 degrees. So here the value is 31 degrees. Okay, so coming back to this question, critical angle of the ray moving from glass into air. Now the ray coming out of glass, that same type of glass. The refractive index formula when you are at the critical angle is equal to N is equal to sine 90 over sine C, which is the refractive index. Here the angle of incidence is 90, it's right angle. Then angle of incidence is actually the refracted angle. Okay, so I swap just like I did here, sine R, so I don't show it much here, sine C. Then I straight away just get to this point here, like here, where I'm having C, which is the critical angle, is equals to sine inverse 1, because sine 90 is 1 over 1.5, because that's the refractive index of the glass. Where is it? It's right here. The 1.5, which is the refractive index of the glass, then 1 over 1.5, then sine inverse over 1 over 1.5 gives you this. Okay, so sine 90 is 1, then our refractive index is 1.5. So my angle, or the critical angle of this glass right here, is 42 degrees. 42 degrees. We're almost there. This is my second last question here. A cutoff question. A transistor can be used as a switch because no current can flow in the collector unless current flows in the base circuit, BC. Okay, base circuit. The transistor can be switched on and off by changes in the base current. Okay, figure 7 shows a time operated transistor switch. Before I even get to that, you have to study the transistor. That's your diode. This is a relay. Sometimes the relay has got dots around the switch and the coil here. Okay, there are usually some dots. That's your switch. 6 volts. That's a rheostat. That's an what's this? A capacitor with a switch. They just look at it around here, and for you to know your way out. And then here I felt like it was supposed to have an arrow like this to show that it's an NPN. It's an NPN transistor, because for the other type of transistor, the arrow points inward, here it points outward. Okay, so the arrow points in the direction of conventional current. Okay, the arrow points in the direction of conventional current, but this one has no arrow. Then some transistors usually are labeled BC. BC, this is, I would say, the value of this transistor, more like the type of some kind, because some of them don't have these letters. But I don't know if it was also appropriate. Okay, I'm sure you are expected to know to say this is your base route, and then this is your collector pathway, this is your emitter pathway. A transistor works when current is supplied here, which is this part here. A small amount of current is supplied, which allows a bigger current to flow from the collector to flow all the way. So current has to flow from this end to the other end. It cannot flow from here across the transistor to this end, which is the emitter, if there is no supply from current, a smaller current from here. So this smaller current controls the flow, okay, the switching on and off, the flow or not to flow of current in this collector. So sometimes I'm sure they will be labeled and they will have this arrow, but this one was a little bit blank. I had a little bit of issues like which path should I take, but anyway, I managed to write something about it. Let's look at it. Describe the action of an NPN junction transistor. It passes electrons from the emitter to the collector when current is applied to the base, which is this base here. Okay, I think that would be my answer there. Okay, describe the action, because apart from the N, negative, positive, negative, you also have a PNP, but this one is an NPN. NPN transistors are much faster than the PNP ones, and that's why they are sometimes that's one advantage why they are used more than the others. So explain how the time operated switch in figure 7 operates to switch on. When a positive signal is applied to the base, it turns on. That was my answer there. Explain how a time operated switch operates to switch on. So for current to flow from this end to this end, a positive input or current has to be supplied here. Okay, a 1, not 0, 1 binary logic gates, but a 1 or a higher value, a higher voltage or a positive input has to be supplied here. Then current to flow from this end. Then finally there will be current in the emitter flowing back to which will also cause this to actually light up because the circuit would have been completed. Explain why 1. A diode is required in the circuit to rectify current flow, thus, protect other components from damage. When you look at this diode here, allow me to move the camera. This is our diode. Current will move, or let me say, electron flow will move in that direction, okay, but it will not move backwards. Okay, therefore, the reversal, a diode is an electric component that allows current to only flow in one direction. And you should understand, like in the next question, I'll talk about this in the next question 8, the flow of electrons and the flow of current. So when I talk about the flow of electrons, this is why this arrow is pointing. It's in that direction. But flowing backwards is impossible, and that's an advantage, because if electrons in one or another flow backwards, then some electrical components like this rheostat here can be damaged, and any other components around. So to protect our components from damage. Okay, and apart from that, when I say rectify, I mean to allow current to flow only in one direction. Okay, and maintain the pattern like that. Explain why the bulb can be operated by a normally open relay instead of being placed in the collector circuit. Because the operation of the bulb is wholly dependent on the relay and not the transistor. At first I didn't understand this, and I hope I'm correct on this one, but when you look at this circuit here, even if this bulb was to be directly connected at this point, when they say normally open relay, like here, normally open relay, this is the type of relay that is always open in default. Okay, it's always open in default, so it only closes or allows current to flow once you charge it. If not charged, it normally remains open. So the thing is, if this bulb is connected here, once the diode does its job, everything happens. My point is, the switching on of the bulb is dependent on the relay. Okay, so even if you connect it directly here, it comes like this. It will still go on and off with no connection to the transistor. But right now it's connected to the transistor and it's getting on the moment the relay closes and current passes through the transistor. But all in all, even if you connect it at this point here, it will still light up because it's wholly dependent on the switch in the relay for its circuit to be complete. For each circuit to be complete. So that was my answer there. You can phrase it in any other way you may understand it, because the operation of the bulb is wholly or totally dependent on the relay and not the transistor. Allow me to do the last question and we'll call it quits, and I'll do the other questions in parts because it's long. The paper is heavy and long. It's a 2-hour paper. So a student rubs a polythene. Polythene is a type of plastic bar with a dried cloth, and the cloth becomes positively charged, meaning this one remains negative. Okay, this one gets electrons from the cloth. That's why the cloth remains relatively positive. The charged remember, protons don't move, electrons move. So these difference in charges are as a result of electron transfer. The charged polythene bar is placed near a stream of water from a tap as shown in the figure here. I don't even know who opened this tap. The stream of the water bends towards the bar. Okay, A1. On the figure, show the charge distribution in the polythene bar. Negative. Okay, negative. Again, let me see. As I was writing this negative here, I was thinking like, do they want me to... Now you cannot label the charge on the water, and this is not how you label negative in the water. If this is negative, then this should be the water molecules are too small. So I was thinking like, if the polythene bar became negatively charged, the cloth became positive, then it is this negativity which is drawing the positivity from here. So I think I was correct, because I was almost thinking like, should I put negative here then positive on the other end or what? But anyway, this is the guy who's charged, so it's negatively charged. It's not in contact with the water, so there's no transfer of charge. So I labeled it with minuses to show that it's negatively charged. Hopefully I'm correct. Number 2, explain how the charge on the polythene bar causes positive and negative particles in the water to move. Water is made of molecules, so there are no positive and negative particles in the water, but the water molecules themselves have regions of positivity and regions of negativity. When you go back into your chemistry, you talk about polar bonding, where one region is positive, the other one is negative. Okay, or let me just say oxygen is bonded to 2 nitrogens. Oxygen has got these spectator electrons, okay, or non-bonding pairs of electrons. Therefore, they cause some kind of negativity to build up, okay, to build up. Therefore, the oxygen end of the molecule becomes partially negative, and then the 2 hydrogen ends of the water molecule become positively charged. So, because of this, water is polar. It can interact with ionic compounds and also covalent compounds to some degree. So because of this, the positive regions are going to be oriented in such a way that they will face this. Then the negative regions of each of the particles in water, the molecules in water, will face away from the bar. So that's what my answer is based on. The positive regions of the water particles are attracted to the bar and negative regions repelled. The lines were too small, I couldn't explain much, but that's my approach right there. Coming back to electricity, electronics, figure 8 shows an electric circuit. Okay, this is your light dependent resistor. Okay, X point F, this is a normal resistor, this is a battery, this is your negative end, that's your positive. Maybe let me just do this, negative, positive. On the figure, draw an arrow at F to show the direction of flow of electrons in the wire. So you should know that there is electron flow and there is current flow. Electrons bring about current, okay, but usually the current flow is opposite to the direction of electrons, and it is so because at first it was believed that protons are the ones that flow. So current was taken to be moving from the positive terminal of the battery. So even right now, it is taken to be moving away from the positive of the battery, and it's called conventional current because it is something that is agreed upon, okay, but the actual flow are actually the electrons themselves. So on the figure, draw an arrow at F to show the direction of flow of electrons in the wire. That's the electron flow. Electrons flow from the negative to the positive. Wireless current is taken to flow from the positive to the negative. Differentiate the two. Current, name component X. Look at the symbol. There's a resistor there. Then there are those arrows right there. Arrows right there which represent light. So it's a light dependent resistor. This resistor gets to have its resistance reduced as light gets brighter. Therefore, it has got a semiconductor that is made up of, or not really a semiconductor, but yeah, let me just say semiconducting material that is mostly made up of cadmium sulfide, if my memory serves me well, cadmium sulfide. And this semiconductor tends to its conductivity of electricity tends to increase as it gets to be exposed to light. So the next question is, state and explain how the potential difference across X varies as light shining on it brightens. Yes, that's what I'm talking about. The brighter the light on X, the lower the resistance. Thus, the lower the potential difference across it. Look at that again. The brighter the light on X, which is our LDR, the lower the resistance. Therefore, it allows electricity to pass. If it allows, the more current it allows to pass, therefore, the lower PD across it. The lower the potential difference across it. That's the relationship between the light and the resistance and the PD across an LDR. My last question in this section is, suggest one way or maybe one use suggest one use of the circuit in figure 8. Suggest one use of the circuit in figure 8 in a light operated intruder alarm. Once someone opens the door, switches on the light, or shines the light on the alarm somewhere along the linings of the door or the lock somewhere there, then resistance in the LDR will reduce, current will flow, and the bell somewhere will ring. So in a light operated intruder alarm, I end here for section A. Hopefully it was helpful in some or another. Remember to just look at the question, analyze them, resolve them if possible. Like the videos, share, and I'll see you next time in the next videos as I look at each of these questions one by one in section B. Because they are big, I'll do them one by one at a time. So have a good day and Happy New Year to you.